Like all equilibria, we can write an expression for the equilibrium constant for the acid-base reactions that takes place when the acid dissolves in water. So here, so let's start. For example, let's say I'm HCl when dissolved in water. Let's say I'm going to write down an equilibrium reaction, and let me change and let me write down this as a um, general reaction. And I'm just going to take in general HA. A could be anything, but HA is an acid, and then when dissolved in water, it's forming acid and conjugate acid and conjugate bases. Now equilibrium constant. So here first it is equilibrium constant. And what is equilibrium constant? We denote it by letter K. It is the concentration of products divided by concentration of reactants. So these are products, these are reactants. So here are the products, and we write down concentration in square brackets divided by concentration of reactants. Uh, Now this is right now K, just K is equilibrium constant. Now, so let me write down the phases. For example, HA aqueous means dissolved in water, H2O is liquid, aqueous. Now, since water is a liquid and its concentration is essentially constant, what we do, if I take this on that side, KH2O equals to H3O plus times A minus divided by HA. And then constant times, this is also constant, is replaced by a new constant which we call it as Ka, which I'm mentioning here, which is known as acid dissociation constant. Now, what is the significance of this Ka, and how is this Ka, acid dissociation constant, is related to the acid strength? The stronger the acid, the higher the concentration of the products of an acid-base reaction, which means the larger the numerator in the reaction. So here, for example, let's take, I'm going to write down any two acids. For example, HCN, hydrogen cyanide, it's an acid. Its value, Ka value is 4.9 times 10 to the negative 10th. If I take another acid, which is acetic acid Ka value is 1.8 times 10 to the negative 5th. Now, which one out of this two is the larger value? This one. And if this is the larger value, means acetic acid is stronger than HCN. So basically, the value of Ka, the acid dissociation constant, can also help you to find the strength of an acid as well as to predict the direction of the equilibrium. Now, how does this help with the direction of the equilibrium? So let's look at that. And let me write down one reaction here. For example, C, let me, C6H8O6. This is vitamin C, reacts with ammonia aqueous to form conjugate base plus NH4 plus. Now here label the acids and bases. On the left side this is an acid, on the right side this is an acid, which is a conjugate acid, but acid. The Ka value of this acid is 7.9 times 10 to the negative fifth, and the value of this acid is 5.6 times 10 to the negative 10th. Now which one is a larger value? This one is. This is stronger, and that means that NH4 plus is a weaker, and equilibrium favors the formation of the weaker acid. Means again you go from the stronger acid side to the weaker. You always go from stronger to weaker. That means this is going to be a bigger arrow and this one is going to be a smaller arrow. So how do we answer that? The products are favored at equilibrium. Let's talk about one more constant, Kw. But let me write down a reaction. For example, water can act as an acid as well as base. So if you look at this reaction, two water molecules, they are reacting to form H3O plus and OH minus. One is acting as an acid and other one is acting as a base. If this is acting as an acid, this is the conjugate base, conjugate acid. So here, equilibrium here in this case, if I'm drawing a bigger arrow on the left side, means the reactants are favored. And why is that? Because if you compare acid, the H3O plus Ka value is much higher than H2O, and we always go from the stronger to the weaker side. Now if I write down K is equilibrium constant, which is concentration of products divided by concentration of reactants, then it will be H3O plus times OH minus divided by H2O. How many molecules are there? 2. So now again in this one, since we know that concentration of water does not change much, and if I take this on the other side, it will be this equals to H3O plus and OH minus. And this K times H2O square, we can replace it with another constant, which we call it as Kw, ion product constant. So this is an ion product of ions, product of H3O plus and OH minus. Since now here experimentally it can be shown that if you take the pure water, then the concentration of hydronium ions is equal to concentration of OH minus. So let me write that down here. So again, in pure water, the concentration of H3O plus is equal to concentration of OH minus, which is equal to 1.0 times 10 to the negative 7th molar and at 25 degrees Celsius. So in pure water, concentration of hydronium ions is equal to concentration of hydroxide ions, which is equal to this. So if I write down Kw, which is H3O plus times OH minus, and again if we are talking about the pure water, 1.0 times 10 to the negative 7th multiplied by 1.0 times 10 to the negative 7th. And if you multiply these two, it is negative 14th. So that means the product here, H3O plus and OH minus, is a constant, and is Kw, and its value is 1.0 times 10 to the negative 14th at 25 degree Celsius. Now, this is a very important equation. For example, let's say the concentration of H3O plus is given, you can find out concentration of OH minus. Or if the concentration of OH minus is given, you can find out concentration of H3O plus, because the value of Kw is 1.0 times 10 to the negative 14th.
Made with Doodlecast Pro.